Okay, a nice word problem to go with this one. All right, we have traces of burned wood along with ancient stone tools in an archaeological dig in Chile were found to contain approximately 1.67% of the original amount of carbon-14. All right, next they give us some information about the half-life of carbon-14 is 5,600 years. All right, so big keyword there, we see half-life come up. We want to know approximately when was the tree cut and burned. So to put this information together, and this is kind of a tricky problem, this is all going to fit into our A equals P times E raised to the RT formula. You may see different variables here depending on exactly how this has been taught to you, but basically I use the banking ones where A is the accumulated amount, what you end up with, P is what you start with, R is our rate, and T is our time. Now where people go wrong here is they don't notice that first keyword, that half-life. All right, the half-life is the information we need to begin with. All right, the other thing that people forget about is they see that 1.67% and they say, so that has to be my rate. Percent is always the rate. It's not. All right, so because we're given the half-life information, we want to start with that. In 5,600 years, that's a value for our time t. So let's plug that in first. We're just dealing with the half-life information to begin with. All right, now carbon-14 is one of these things that you have 100% of it when you're alive. So you start with 100%, but then after 5,600 years, after you've been dead that long, you're only going to have half of that original amount remaining. So our accumulated amount is just going to be 50 as we initially set this up. Again, remember I said we don't know our rate. That 1.67%, that's going to come up in a little bit. So let's plug in the information we do know about half-life. So when we plug this in, we're going to get 50 goes in for A, 100 goes in for P, E raised to the R is unknown multiplied by 5,600. Okay, so we have an exponential equation. Let's isolate the exponential part, the E raised to the power. That means this 100 that's out in front, let's move it to the other side by dividing it because it was connected with multiplication. Now you may notice that we get a 1/2 with a little reducing down on the left-hand side is E raised to the R times 5,600 power. All right, next we can either use the definition of logarithm to switch over to logarithmic form, or what I like to do is I like to apply a natural log to both sides. My reasoning is natural log is log base E, and we have a base E on the right-hand side that's pretty evident, hopefully. And what's going to happen is we're composing together an exponential function with base E and a logarithmic function with base E. We're going to get some nice simplifying down on the right-hand side. So natural log of 1/2 on the right-hand side, or on the left side, we're going to have R times 5,600, just our exponent remaining on the right side. From here, we want to isolate R and get it all by itself. It's multiplied by that 5,600. So let's go ahead and divide both sides by 5,600. This will put R on the right-hand side all by itself, and this will be the exact rate that we're going to utilize. All right, so follow-up question. We've done a lot of work. We found our rate. Let's use that rate down here. So I'm copying and pasting our natural log of 1/2 divided by 5,600. We want to know how long ago was this tree cut and burned approximately. All right, so back to our information, only 1.67% of the original amount of carbon-14 remained after they tested it. So what that's going to be is 1.67% is the amount that remained after we dug this up. How much did we start with? Well, again, when it was alive, it had 100% of its carbon-14, and we want to know this time frame, right? We don't know how long, right? That's a question about time. Same formula, 1.67 equals 100 was our starting rate, our starting amount, E raised to, and I know this looks messy, but natural log of 1/2 over 5,600 multiplied by our T, that's all up in the exponent. So kind of the same steps as we move forward here, trying to get T all by itself. First, I'm going to isolate the E raised to the power. So I'm going to divide both sides by 100. All right, in doing so, that's going to move the decimal place over 2 decimal places to the left-hand side. So 0.0167. On the right-hand side, these 100s are gone, right? Multiplying and dividing by the same thing. And we're going to be left with e raised to that natural log of 1/2 divided by 5,600. That's all up in the exponent, as is the times t. Pretty similarly to that first one's, what we're going to do next is use a natural log on both sides because our base is e. And why I'm doing it instead of getting like a decimal approximation for that rate is this is going to be a more accurate answer. All right, so natural log of 1/2, 5,600 times t, all up in the exponent, but it's about to be out of the exponent because we use that natural log. So we're going to get natural log of 0.0167 is going to equal the natural log of 1/2, just copying down our exponent over 5,600 times t. Now the remaining process to get that t on one side by itself, I'm first going to go ahead and make this, I'm going to make this 2 steps. I'm first going to go ahead and multiply by the 5,600. That'll eliminate our fraction on the right-hand side. So now we have 5,600 natural log of 0.0167 equals the natural log of 1/2 multiplied by t. T is being multiplied by that natural log of 1/2. To get rid of the natural log of 1/2, we'll divide both sides by the natural log of 1/2. This will get us t on the right-hand side as I've written it all by itself. This is an exact answer that we've got over there on the left side, but we can get an approximate answer. It's going to be maybe squiggly equal signs to mean approximately 33,062.4, and I guess that's years ago that this tree was cut and burned. So I hope this helps out as you're working with half-life, trying to create these equations, these mathematical models that go with the situation, and then solve them down. So start with the half-life, set that one up first, use that information as much as you can. After you're done with it, use the additional information to set up the rest.